Dear colleagues, dear friends, good afternoon. My name is Andreev Alexey, and I represent Kazan Federal University, which is in Kazan, Russia. And the theme of my today's report is the study of the digital model of the Earth built on remote sensing data by ASTA system. My co-author is Nefedi Fury. So the first question that I would like to discuss today is why using fractal analysis. Currently, when solving a number of tasks of Earth remote sensing, we use multiple technical tools for observations that can operate in different wavelengths. I mean satellite and airplane systems, as well as observations made by naval and ground-based observatories. And the information that we produce using those systems could be presented as separate or consequent in time images of some terrain. And those are frames that could be processed in the future in order to extract some useful information about the objects on those images. In order to analyze those images, visual, spectral, and counter-texture methods are widely applied. But still, the main and basic method for processing aerospace images is visual one. And in doing so, we have to deal with large volume of data as photo and video material, which leads to low temp of information processing. And the recent studies have shown that it is possible to apply the theory of fractals in order to solve the tasks of Earth remote sensing. As a source of information, we use the data by Aster radiometer, which was installed on spacecraft Terra, NASA. This project was launched back in 1999 by NASA together with Japan Space System Organization and Ministry of Economy, Trade and Investments of Japan. And this project Aster covers Earth in 14 ranges of wavelength, from visual to thermal infrared, from 83 degrees of northern latitude to 83 degrees of southern latitude. The spatial resolution varies depending on the range of wavelength. For visual and near infrared, it is about 15 meters. For short infrared, it is about 30 meters, and for thermal infrared, it is about 90 meters. And each separate image covers an area of 60 by 60 kilometers, and the total percentage of cover is 99. In order to build hypsometric or elevation model, we expanded the data by Aster in a series of spherical functions. There is a relation between function of altimetry, which depends on latitude and longitude, with harmonic amplitudes, associated Legendre functions, and random regression error. After that, for this model, we determine fractal dimensions, and different types of surfaces are described as a combination of areas which are characterized by certain number in the range from 2 to 3, which is called fractal dimension. In our work, we considered latitude sections, and the straight line corresponds to d, which is equal to 1. But in our case, because of the fact that Earth relief at some points goes up, in other points it goes down, we produced curves, and their fractal dimension we determined in this work. The essence of the method is as follows. We have Euclidean plane, which is divided into squares with a side of sigma by the lines which are parallel to coordinate axis, and we consider a limited set, which is m in our case, and in this case n is the minimum number of covers for the area studied, and the total number of n covers the whole set M. In the general case, the dimension of the set M is D if at sigma common to 0 the number of covers grows as the relation of R to sigma in the power of D. In this case, R is called the D measure of the set M, and then the fractal dimension D could be calculated by the formula which is given in the lower part of this slide. For the first time, we applied this fractal method to the moon, and this study was published in the article which is given in the lower part of this slide. We considered 4 models of the moon's surface. The first model was classic one. In this model, the points of the limb are bound at given libration to the Merstring A crater. The second model is the one by Yukovkin. This model considers the thickening in the vicinity of the southern pole of the moon. The third model is by Rahimov. In this model, the points of the limb are bound to stars. And the fourth model is made by or on the basis of Kazan's heliocentric catalog. And as you see, for different ranges of position angle, we determine fractal dimensions, and they are in good agreement with each other. And considering the fact that those models represent the same parts of the moon, this method could be considered reliable. The same method we applied to Mars. We have already published this study in the article which is given in the lower part of this slide. We considered again 2 models. The first one was elevation model, and the second model was gravimetric, when we consider the variations of the gravitational field. And for those models, we determined fractal dimensions depending on latitude and longitude. And also the same method we applied to Venus. We analyzed the surface of Venus and gravitational field. And for those models, we also determine fractal dimensions. So, on this slide, we present the dependence of fractal dimension of the hypsometric model of the Earth depending on geographical latitude. And for the Earth, the average fractal dimension is found to be 1.178. On this slide, you may see the average fractal dimensions calculated for all the investigated celestial bodies. They are given in this table, and we highlighted those dimensions for the models which fit each other the best, or that are found to be in the best agreement with each other. And as you can see, the fractal dimensions for latitude models of Mars, Venus, and Earth are very close. After that, we decided to compare our result with the results by other authors, and we analyzed literature and found that Turcotte, famous scientist, determined fractal dimensions for 2 models of the Earth. The first model was geoid, the second model was the classic topographic models, and these models were analyzed, and for them Turcotte found fractal dimensions. For geoid it is 0.75, for topographic model it is 0.81. So our result is correlated to the result by famous author and famous study which was published in the Journal of Geophysical Research, Solid Earth. So to sum up, we may draw some conclusions. The first conclusion is that we considered a new method for studying maps of celestial objects. The second conclusion is that we determined the mean fractal dimensions of topographic model of the Earth, and the comparative analysis has shown that fractal dimensions for the models of Earth, Venus, and Mars on latitude are very close, which means that their surfaces are similar. And also at the moment we are finishing the work on calculation fractal dimension of the Earth on longitude, and we are planning to apply the same method to Mercury in order to make our study more representative. Thank you for your attention. I was very glad to give this report. Thank you.